So, lesson 3, we are going to continue exploring the syntax of and the structure of Solidity smart contracts. We're going to continue from the same exercise we had yesterday from the hello world.sol. I'm going to use this for explaining most of the concepts that we need, the architecture of the EVM, smart contracts, and blah, blah, so that we don't have like a boring lesson. Every time that we go through the documentation exhaustively, one by one, we might understand in theory what's going on, but sometimes we are not sure if we have fully understood what is happening. So with this exercise, you're going to see all of those concepts. We're going to see all of the, sorry about that. We're going to see all of the Solidity types, the memory architecture of inside the storage architecture inside the smart contract, the accounts, the control structures, and all using an exercise, a guided exercise that should be more engaging for us to follow. Okay. So we saw that when we send this transaction for the blockchain, it's going to take a little while to be included. And when it's included, it's going to change the state of the blockchain from state A to state B. Okay. And whatever is going to determine those state changes is the bytecode stored in the blockchain. Okay. We saw that. And here what we are doing is programming this function setText in a way that we can change this variable there inside the blockchain when calling that function. We cannot change that value directly. We cannot go there and do like a ETH transaction, Bitcoin transaction, whatever that changes that value. We need to go through a function, and this function is going to govern the change of that data. This is what makes the blockchain so safe and secure at the end of the day. The program is protected by all of the cryptographic assurance of the blockchain. This transaction is taking way more than I would expect. I guess it did confirm. Yeah, confirmed. But you don't like this scan? That's crazy. Maintenance in progress. Oh, that's so funny. That's good, yeah. Oh, dang. I needed to use this information, but okay. No worries. So let me pick one of those older transactions that we have here. What happens when we have one of those state changes? So there is a smart contract, and then I have a place in the smart contract. Yes, I don't store it globally, the whole blob with the smart contract. I have several small places. We train to see smart contracts as are like you have an address, and then you enter the address, you have just one thing there. But actually, no, each smart contract is a collection of places inside of it that it can store more things. It's like the address of a house or the address of a hotel. The address of a house, there's just one person, one family there. But if you go for a hotel, you have hundreds, dozens, or hundreds of different rooms there. So these would be those storage addresses here, where we can change this text from potato to tomato, like we have here. Okay. So I don't have the recent transaction, but I can use those older transactions to explain. So what is happening here is that inside these accounts, I'm going to have a collection. Each of those accounts is going to have a collection of objects. One to store the code of that smart contract that's going to be invoked when processing that transaction. And another would be a persistent key value store mapping of 256-bit words to 256-bit words called storage. What is that? It seems very complex, yes, but I can show one example here. We were seeing that just now. This is a 256-bit keys that I can change to up to 256 bits of content here. Okay. This is what we have here explained. This would be the persistent key value store mapping of 256 bits worth. So when Naya was answering the question about the smart contract, what this is a state variable now. This state variable under the hood, Solidity is great. Solidity is dealing with all of that for us. Under the hood, it is creating a place in that persistent key store, mapping all of those pointers, putting an accessor for it, managing the boundaries of it, truncating the chunks of where I should get everything for us now. So there is a lot going under the hood. And here, what we see, just one line of code. Just one line of code doing this, and then another line of code doing that. It's very high level. There are hundreds of operations being taken care under the hood when we do this. And let's look at one technical detail that might be very enlightening here. So because we have a persistent storage inside these smart contracts, and writing for this storage is costly. There's storage as we have here, for example, writing to this is very costly. I'm looking for the correct link for this. Just 1 second. Storage memory in the stack. This is what I'm looking for. Here's the change storage. Okay. Link, broken link. I'm going to fix that. Because everything that we change in storage is so costly. Those words here, whenever we change it, it is costly to read, it's costly to write, it's even more to initialize and modify storage now. So we would avoid using this storage whenever we can use something more transient. For example, the memory, that is the normal space that we would deal with things, that would have width of 250 bits, and I can swap it back and forth when doing these operations. The bytecode handles all of that for us. And we have a place called the stack where the operations happen. And understanding this memory and stack correlation and operation can be crucial for you to optimize gas costs. It's not something that we're going to do today. I'm just explaining that this exists, okay, just so that you are aware of that, because it's not only because your smart contract is working that it is correct. Maybe you are doing many more operations than what you needed, because you are not aware of what is happening under the hood. For example, whenever we are, let me pick the smart contract again. Whenever we are storing set text here, whenever we're storing this new text with this string of the type memory string, we are wasting a little of gas. Let me explain you why. We saw that strings are arrays, right? Every array is something called a reference type that I can deal with it in the storage, in call data, or in memory. I have those three options here. Must be memory, call data, or storage. Storage cannot be used here because I'm receiving something from outside of the blockchain. Cannot be used here because I'm giving something for outside the blockchain. We're going to see next week an example of using the storage pointer directly. So basically here we have two options: call data or memory. We use memory just as a cheap way to get around this in the first two lessons, but finally I'm going to set a time to explain that. Whenever we are setting a text from memory, we are copying this value that comes from outside of the blockchain to the memory, and then from the memory we are putting that in the storage. Let me connect to my virtual machine here. I'm going to deploy that smart contract and show the cost for you. We deploy. Let me change this text to ABC, set the text, okay? And that operation cost, I have the guess, it cost 300, didn't copy correctly, 32,235 guess, because of all of these operations, picking this value that comes and all. But interesting fact, this information that I'm passing, this ABC value that I'm passing, is already included in the input. This input is stored in a place called call data that can be used directly without using the memory. It's there, the stack has access to it. I cannot change the value when I use call data. I'm going to explain that in the future. But whenever I use it directly like this, call data, I can save some gas. Let me deploy the second version of it, now using call data. And I'm going to change from hello world to ABC again. Now this transaction, the same transaction, the same change that happened in the blockchain in a different address. Sometimes the address also impact the cost, but this is something else. Cost 31,705 gas. Just because I'm using the information directly as it comes from call data, okay? It is a neglectable amount of money if you put that into convert into ETH. Depends on the price per gas. You're going to see a lot of that in in week 5 actually. This is another thing, but for now we are spending more gas. Okay, we are the car is not as efficient. Imagine like that. Okay, so I'm not going to explain fully what is happening here. This is about gas optimization now. I just want you to be aware that all of these brushing bytes that we are doing, explaining the depths of EVM and all, it is much needed because there's so much going on behind the scenes here under the hood that one single wrong definition can cost hundreds of dollars, if not thousands of dollars. If it's a hack, billions of dollars from your end users. And this is not something that we should take lightly. Okay. Now you have a question.
I did, but I think it might get answered in a future lesson, so I'm gonna hold off.
Okay, okay. If it doesn't get answered until the end of the bootcamp, ping me. So this call data has a little uh, um, um, limitation. That is, I cannot change the information. For example, if I want to multiply or append or whatever, I cannot, for example, I cannot put new text equal to something else. It wouldn't work because new text needs to be call data. Okay. If I put that as memory I can. I can freely edit it at any point, you see? So that would be the difference. Okay. Questions here before we proceed? This call data stuff. Today I have two things to demonstrate. Would be these exercises here. I'm going to use that to explain assertions and modifiers and all in global variables, so that we prepare for tomorrow for the weekend project. Okay. I'm going to do those step by step, but you have the whole code here if you want to edit. If you want to edit, if you want to follow, and I'm going to edit part by step by step, but if you want to go in one go, you can. I'm going to change the line 13. Instead of having text equal to hello world, I'm going to have this function called initial text that is going to be called from the construction. Like this. Let me clean it up a little. So question here, what are the possible visibility options for initial text for this code to work? What are your guesses? Pedro,
In this case, I just looked at the function now, but it seems like it's not changing any blockchain state. I would use pure like you have, but I think
okay,
technically you can use any of them, but you're not supposed to. I think you just get a warning and not a compilation error.
okay. It's state mutability, right? Maybe I did not express me correctly. I would ask the visibilities. What options of visibilities can we use here?
Oh, like public, external, private, etc. Oh,
Yeah,
those I don't remember so well, but
let's use that for recapitulating then. Let's see
yeah,
if we can use external. Okay,
you
what
can use
happens if
external,
we use
but then you
external?
cannot call it inside the contract.
Good. So can we use internal? Okay, it works. Can we use private? Okay, it works. So my intention with this exercise here is for us to consolidate this knowledge. I can even do another append here of like 5 minutes or so for us to consolidate these visibilities here, okay? And I want you to have this practice every time that you want to remember about one of these things, you can come here and call this quickly. So I'm going to do another smart contract called inherited hello world. And I'm going to inherit from hello world is hello world. Similar to what we did with the interface. We did that with the interface yesterday and today early on. Now I'm creating another inherited hello world. Okay. And I'm going to deploy this inherited hello world. How many lines of code I have here? No lines of code, right? But if I deploy this inherit hello world, I have everything that hello world has. I have hello world that turns hello world, I can change text and all. Well, let's play with some things. Let's create a constructor here. And let's make initial text equal initial text again. Now I have two problems. I cannot see text and I cannot see initial text. You know why? This is a very technical detail from some things that I explained, but
It's
let's see if
private
you,
functions.
because they are private. If I put as internal, it would work. Internal, internal, then it would work. You see? What could I do without changing this smart contract? I could call set text to something in the constructor. This I can do. Set text to potato, for example. It needs to be call data. Yeah, so I've locked myself out here. It needs to be in the call data. If I put in memory, it would work. You see, so if I deploy hello world and if I deploy inherit hello world, this is going to be hello world and this is going to be potato. If I set the text in one, tomato, it changes here, but of course it's not going to change there. Those are two different addresses in the blockchain, okay? And now let me do a very tricky one. Put that in call data. And I'm going to change initial text. I'm going to change the function initial text to do something else. Hello there. So the inherited hello world is going to inherit from hello world, but is going to change one function. For that, I need to mark this function as virtual. I mentioned that very briefly about virtual contracts that they can be overridden and all. And this one I need to state that it's overrides. Okay, pure. Of course, it's not private. It can be like public or something like this. And this is going to be public too. So this one is going to be very tricky. I'm inherit hello world from hello world, bringing all of the code from hello world here. And I'm overriding the initial text definition for hello world as hello there. Now I'm going to deploy those two smart contracts. I'm going to deploy hello world, and I'm going to deploy inherited hello world. What is going to be the initial text of hello world, and what should come out of here? We inherited, but it is still a different entity. So any changes in inherited members, they don't change anything in the inherited one, in the ancestral. This is okay. But what is going to happen here in the inherited hello world? We did not change the constructor. The constructor is equal to line 8. Text is speaking initial text, as we have here in the line 19. So is the initial text from inherit hello world is going to be hello world or is going to be hello there? What do you think? I have Laurent.
There.
I have Peter. Oh, hello, Marco. You're saying hello here? Just kidding. It's hello there, General Kenobi. Okay, because it's picked the overridden version of the initial text and use it there. Okay, so latency has a lot of this too. So it is designed to target the EVM, yes, but it also designed to help you in the development life cycle of this smart contract who can access your code, who can do things on your code. So it is built for composability too. Okay, it is built for restricting and enabling access of things for the developers. It has nothing to do with information on chain, with your crypto balances or anything else. It is only pertaining about what you can do as a developer or no. Okay. So that it has a lot of things like this too. First person with the hand raised, it would be Laurent. You have a question here?
Yes. When you deploy the contract, you don't sign anything in MetaMask. Yesterday or 2 days ago, I remember that you were signing anything, something. So my question is, when do you need to sign with your MetaMask and when you don't? And yeah.
Okay, this is about the environment that is configured. I have changed for the virtual machine environment where I have this list of pre-funded accounts that we used in lesson 1 and yesterday, so that I don't need to sign every time, you see?
But you spend every time, right? Every time you deploy, it has a cost?
It has a cost paid by those accounts, those pre-funded accounts, those fake accounts. It doesn't use my MetaMask at all.
Okay. Okay, thanks.
It's very, very convenient for deployment.
And second question is, when you set a new value in your text and you want to assess the new value for demonstration, because I think you're going a bit quick for a bit fast for me, where do you see the new input?
You're asking about these values here in the bottom?
Okay, I didn't see this. Okay, and okay, can you make a new example just to change the value again? And
Of course.
potato,
For example, I'm going to
apple,
change that for ABC.
yeah.
And the initial text is still the same. The value of this function initial text is still the same, but the hello world function changes for ABC.
Okay, okay.
And also I want to demonstrate that inheriting a contract has nothing to do with the storage of the other contract too. Because even though I changed this one for ABC, this order is still hello world. You see, those are different addresses. They don't have anything to do with each other. Okay.
Okay, I didn't saw the place where it was displayed the value. But I'm
Okay.
not so used to this IDE, but it's clearer now. Thanks.
Okay, good. Slowly we get there. We get used to it. Next in line, I guess, is Martin. If I got that correctly.
Yes, you have. I was just wondering, like, the end result of the inherited contract returned hello there, but on contract deployment, was it first set by the base class to hello world and then changed afterwards by the inherited to hello there, or was it initially directly set to hello there?
Okay, this is something that we're going to explain more tomorrow. The thing that happened is that the constructor is the same. Text is equal to initial text, the same function, but the signature for the function initial text changed. So it is something like this. Every time that you arrive home, you put your coat in the hanger. Okay, the coat hanger. Every time you arrive home, you put your coat there. But someone changed the coat hanger from the left to the right. So you arrive home and your coat falls in the ground, you see? Because you are so used to putting the coat there when you arrive at home. So this construction is calling the function initial text. It doesn't know if it's going to target the function in the line 19 or if it's going to target the function in the line 25. Someone changed it there. I'm with closed eyes, but I'm going to call it anyway. I don't know what is there. So what happened is that this line of code 8 called, but we changed this pointer. Instead of calling the function here in line 19, we are calling the function here at line 25. The constructor doesn't know that, but it's working that way. So the initial text is not being written 2 times, hello world and then hello there. It is being written once only.
Okay, yeah, that's
Okay.
just in some object-oriented languages. If you have a base constructor with a default constructor with no arguments, it is called first before the constructor of the derived class. So that is an exception in Solidity now.
Actually, it happens there in Solidity too. It's just that the constructor here is not doing anything else. But I can do another constructor, something else is going to happen, and then it would call super. Okay, we're going to see some examples of this later. And this is going to become more clear tomorrow when we see the function signatures. Okay, for public, for external, and also internal functions. Tomorrow we're going to see that more in depth.
Okay, thanks.
Okay. Next in line, I have Ayodeji.
Yes, sir. So my question is this because we have our constructor as special test? That's why we have LOD, or because we have override in our 925?
Yeah, this is just technical detail. You need to, for overriding a function, you need to have virtual and override. I mentioned that very quickly, but now I'm showing that with time. Okay.
Okay, sir.
And Browns, you have a question?
Okay, yes, I have a question. Okay, you were talking about the 2 functions. I just wanted to make clarity. Is it because of the override the virtual that it has its own difference, or what makes them different? What makes them different? Sorry.
It's just the return value that are different.
Okay.
Okay, good. So let me get to this example as I have here for this exercise, and we're going to interact with these functions to review all of these different aspects from lesson 1, lesson 2, and today's lesson. Okay, and if you have more time, you can do that at home too. I'm going to deploy that hello world. And now I have this initial text function that I demonstrated, and I have the hello world, it's currently hello world. I can change the text normally, ABC, and it's going to change this, but it's not going to change that. Everything that we have done so far. But now I have those two functions. A function to check if the text has changed or not, and a function to do the check itself that would be internal. I could have done that in a single function, of course. Return this and that, and it is possible. I wanted to do in two different functions to show a pattern that is very common called encapsulation. You have a public function that is able to call an internal function or a private function. You're going to see this pattern a lot. So when I call this text has changed, it is saying true, because right now the text changed. If I set it back for hello world, text has changed, it's false because I have put it as the original value. Okay, this is what is happening. And I have a lot of different techniques to explain here. First of all, I have a Boolean as a return value, different from the string that we had here. Now it's a Boolean. It's not a reference type, so I don't need to specify where it's stored. It should be memory anyways. And I have a named return value like this. Whenever I name the return value, I don't need to explicitly say return value like this, because it's not needed. So this is going to do that for us. So imagine situations where you have 2, 3, 4, 5 things that you want to return. Instead of keeping all of those in memory and handling those and operating those, you can just declare those as named entities in the return statement. And Solidity is going to take care of them for you, and you can return them all later. Just as a naming convention, usually we put an underscore after things that are being returned and an underscore before things that are being called private. Okay, usually private members, internal members, they have an underscore before, and things that are being returned, they have an underscore after. Okay, just naming conventions. And what is this thing here in the line 24? This whole comparison thing. This is a detail about the strings. We do not have any string manipulation function embedded there in the language. There are a lot of third-party strings library. We're going to see some of those by the week 5 or week 6. But whenever we want to compare a string, we can compare using the hash of those strings. This can this can almost assure that those are equal without looping for all of those members, because we don't have any length or index access in the string itself. So if the hash of the string A it's equal to the hash of the string B, almost certainly, instead of believing on hash collisions, we can almost certainly say that these are the same strings. A and B are most probably the same string, because the probability of a hash collision is almost 0 in these situations. Okay. Also in this exercise, I have this function restore, that whenever I put something here like ABC, that would change the text for this. Text that changes true. When I click restore, this function is going to call this restore, setting the initial text to text. Look, they need the text to initial text actually. So hello world returned for being hello world, and text has changed is false. If I change for something again, text has changed, true. But if I restore again, went back for this. Okay. So text has changed and restore. There are two examples here of different return types, different operations that we can do inside this smart contract. This does a small exercise. If you have more time, maybe you can try this at home too to see how this is built. Okay. Questions about those two functions, what they are doing? See a lot of talk here in the chat. Okay. Yes, Marco?
Just a question, maybe I missed the point, but why the two functions are split? I mean, you say that it was possible to encapsulate just in one function, right? Why it is split?
This is a pattern called encapsulation. It's not a very good pattern like for saving gas or anything like that. It's just that it's very common to see. So for example, picking the normal ERC20 implementation, you have a private total supply, you have a private name, you have a private symbol, you see? And then whenever you want to call the name, it's a public that returns this. Symbol is a public that returns that. The name of this pattern is encapsulation. I'm showing that today because it's very common for you to do it like that. Because usually when we're building a smart contract, you're building it modular, composable, and you want people to inherit from your smart contract in the future usually. So using this kind of control access, access control, variable control can help people inheriting from smart contract to know what they can or what they can't change. Okay, it's easier for them to not to break stuff if you prepare those structures, you know. Okay. Arda, you have a question?
Yeah. So do you think it's a good idea to mark the is changed function as virtual and text has changed as override?
Okay, it's not
And
possible to
also-
do that inside the same smart contract, right? You would need to do that from other smart contracts, you see?
Yeah, sorry. What I meant was, I'm rephrasing the whole question. Mark is changed as private, and then text has changed as public virtual. So
Yeah,
that in the next inheritance, nobody can access the is changed function. But
yes,
text has changed might be overridden.
public virtual. This would be the perfect implementation for this encapsulation. Okay, very well noted. Because then text exchange can change, people can override it, and isn't changed, it's private, so no one can call it directly. Okay. In this situation that I have here, people would be able to call it isn't changed directly. They would be able to call text change, wouldn't be able to change text change. Okay. Good. There are so many conversations here about the gas stuff. The hash. Okay, yeah. We're going to see gas optimizations in, there's a whole lesson about this security and gas optimization in week 5. No, week 4. Week 5, I guess, if I recall it correctly. Okay, there is a little detail here in this restore function, which is going to introduce us to the assertions and modifiers. Whenever I have the text has changed as false, hello world is still hello world, and I click on restore, if it isn't changed, return false. But since this function is non-payable, I still pay gas. There is no way to put like a conditional view function. Maybe view, maybe non-payable. There is no way like that. Like if the is unchanged, and then make this call view. There is nothing like that. Why? Because you already call this function as a non-payable. You cannot discover that it is a view function in the middle. The way that those smart contracts are designed is that you already call them as payable, as non-payable, as view, as PO directly when calling. So even if you go there in line 36 and discover that you don't need to change anything else in the blockchain, you will still call that chain as that function in the blockchain as non-payable. So you already forward the gas for it. So the only state change that's going to happen is you paying a little gas for someone else to mine that transaction inside a block or to put the transaction inside a block for returning false. You are paying a few cents, just return false. I'm going to click on restore. It's going to return false here. Output was this, was false, and I'm paying. You see? Does that make sense for everyone? Since this is a non-payable call, I'm calling the restore function. Text has changed is false. Hello world is already hello world. So restore is going to do nothing. It's going to just return false. But even though I pay, there is a way to stop that. There is a way to revert. There is a way to reverse the execution with this error handling. You can assert condition, you can require a condition, or you can ask the contract to revert. So that this would stop the execution of the transaction, would revert it to the initial state of the blockchain. It would pay the gas for up to that point. Yes, this is true, but at least you don't pay anything else. And more, if you try that from MetaMask or for normal wallets to call the blockchain, you can even estimate gas first and determine that this transaction is going to fail. So if it isn't changed, I can put like this, revert. Okay. Or I could phrase it in another way. I could say require a condition, and the condition would be not isn't changed. Or I could require text has changed. Be more semantic, right? Require that text has changed. If not text has changed, this function is going to revert. Okay. Pedro, you have a question?
Yeah, that revert function, like it triggered me because the first thing I'm thinking of is there needs to be a mechanism to prevent overuse of this function, because if not, you'll just put revert everywhere to make so you never pay for gas. So how does that work?
Well, you don't pay for gas, but also you don't change the blockchain, right?
Yeah, but okay, so if you can only use revert if no state change to the blockchain has been done, right? If the
You can use
computation
you can
notice
use reverse if computation has changed, but what reverse is going to do is revert all of the changes back to before the transaction. So it's going to undo all of the
But
changes.
then there's like an attack where I can ask them to do like a lot of computation just to waste their resources, and then I put do revert, and then it's like, oh, I won't pay, like I just wasted all your compute power. Sorry, it's
Yeah,
the
but
cybersecurity guy in me. Like,
yeah, but you pay up to the gas that you use it to that point,
oh, okay.
and you don't make any changes. So it's the worst case scenario for you
Okay, you
because you
still pay
pay
for
for the
gas
whole.
even if you do revert, if state changes to the blockchain were made, right?
Yeah, you pay for the gas up to that point, not
Yeah, yeah,
only
yeah.
for the state change, but you pay for everything. All the computation that happened up to that point of reversion, you pay. The
Okay.
trick here is that you can simulate that function before you even send to the blockchain. You simulate it in a local node. It's very common to happen. And then you see how much gas you're going to pay. If it is reverting, you can even refrain from sending that transaction. You know?
Okay. Yeah, I get it. Yeah,
Let me
thank you.
show how that would work. I'm going to connect my MetaMask and connect my MetaMask. Okay. And if I'm going to deploy that smart contract, it's going to pop up the confirmation here for me to pay the gas, right? We saw that already. Let me cancel this operation. But if I put a revert here in the constructor, this is possible. If I try to deploy that smart contract, look what MetaMask is going to say. Oh, the gas estimation errored. So this transaction is likely to fail. Do you want to force sending anyway? I could. So this would save gas. Whenever you have a situation that is reverting, the end user would refrain from sending. Because if I send this transaction, I'm going to pay for the gas up to the reversion point. See? And there are 3 different ways to do that. That is the revert and require, semantically different. Like if something happened, I revert, or I require something. They do the same thing, but in different positions. You position the question differently. And assert that would be to check invariance. If an assert failed, you're going to panic. It's dramatic. Okay, that is a different kind of error. So asserts are for things that are like invariants. Constants should be like that, and then you assert this constant. And require are for things that are normal to happen. The client comes and it doesn't have money to pay. Okay, don't panic. You just decline. Okay, I cannot sell you that because you don't have money. Okay, the client comes and they don't have the membership card. Then you require. Okay, don't panic. But the client comes and you look at it, it doesn't have a head. Then you panic. You assert. Usually the person has a head on it. Maybe it's Halloween or something like that. So assert would be for some things that you would panic if it's not there. Acquire are for and revert are for things that are normal to happen. Okay. Makes sense? Laurent, you comment that it's not clear for you.
Yes,
Then
no,
maybe
it's not clear for me. In which case we may need to revert concretely? Sorry, maybe it's obvious for everybody, but not for me, excuse me.
yeah, for example, here, the person is trying to restore a text that didn't change. So I require the text to change. Otherwise, I'm going to revert. Otherwise, I don't want that person to waste money, you see?
But why not preventing the text to change at the first place?
How?
To make it private, for instance, no?
No, here what is happening is this. Let me go back for the virtual machine. I want the function restore to happen. So let's see what's happening. My remix froze here. Sorry about that. Let me restart it. I want the function restore to work in certain conditions. I want it to work when the text has changed so that I can restore it to the initial text. But I don't want it to work when the text is already the initial text, not to waste money from people. You see?
Yeah,
Hello world here. Compile. Now I'm going to deploy. So the initial state of this contract is like this. I have hello world here that is equal to the initial text. But if I set text to something different, like ABC, hello world changed for ABC. The initial text is still the same. Text has changed, it's true. So I want to be able to restore it to hello world.
Okay.
Okay, good.
Okay.
But what I don't want is to call it again. But now it reverted. Now I have prevented the execution, prevented this flow here, okay?
It's clearer. Okay. Thank you. Thanks.
Good. Yeah. Browse, you had a question too?
Yes, I have a question. Okay, so the revert function, I wanted to know when we use it under the function restore, is it going to still change it from hello world, from changing it from the initial whatever called string?
Yes, I've used it restore just as an example here. So
Yes.
this is going to change from something else. For example, I have A, B, C, D here. Hello world is now A, B, C, D is different from initial text. So text has changed. It's true. When I click on restore, it's going to go back for the initial text, you see? So text has changed, it's now false. Okay?
Okay. Yes, I understand. Thank you.
Okay, good. So usually whenever we have these situations, we put it inside a technique called a modifier. We're going to use that a lot tomorrow. That is language technique. It doesn't get actually deployed to the smart contract in any way. It's just like a language technique, so that you would append or prepend this code inside another function. So, for example, we have this function abort, but has this modifier, only seller. So this modifier is going to put all of this code block before the function. Okay, so the amended semantic that can be either before or after or in between surrounding the function by this symbol would jump back to the function, would apply this for all of the functions that you put this modifier on. So for example, I can pick my remix. Instead of putting the require here, I can create a modifier like this, modifier only when text has changed. And it would require text change it. And then it would come for the function. And then I can append this here, public, only when text has changed, turns. This gets a little more semantic. This doesn't get, the modifier doesn't get deployed to the blockchain, okay? For the EVM, this function and these functions are the same. For the deploy bytecode, it is the same, but for readability purpose, modifiers are more like readable, but the contract is going to do the same stuff, okay? Good. Trust, you raised your hand a while ago. You have a question?
Yes. I really didn't get the difference between that assert and require. I understand required well. Like it is like you check for a particular condition. If let's say like for ownership now you can say okay is this the owner of this wallet for that wallet to be able to perform a particular transaction? I get that, but for the assert I really didn't get what assert does and how it works.
Trust, I'm sorry, but it's very difficult to hear what you are saying.
Okay, hello, can you hear me?
There is some background noise, it seems.
Kind of bring me here.
Maybe you want to type a
Okay,
question. I pick it later. Okay, in the last part for today's lesson, in these last 3 minutes, I'm going to review that tomorrow too, would be for the global variables. We have some variables that we can access in the context of a transaction call or the block information that we can use inside any function calls or any variable operation blah, 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 that we're using inside the blockchain without explicitly defining them. So for example, picking the block hash, picking the transaction number, the transaction hash, the block timestamp, the transaction gas price, the MSC sender, we can do all of those operations Remember yesterday when I was explaining payable that I demonstrated very quickly that is MSG value. So I can use all of those defined global variables inside my smart contracts when doing operations with them. So common values for us to use are those transaction properties. That would be the MSG sender, the value, and all that is being sent for that transaction, the gas is being, I can use all of those properties. And the block information, that would be the block hash, the block number, the randomness, the difficulty. There are many other characteristics that we can use. Okay, tomorrow I'm going to review more about this. Today, I guess we went through a good amount of content already. Trust, now I see your question. You didn't get the explanation of assert. So here we have been using require and revert. Okay, require and revert are like normal errors that are normal to happen. But assert would be for some things that you need to make sure that are there and can never fail. If something fails, you would panic. So for example, let's say that my contract always has a balance and it needs to be above that or at least that. I can assert this. If it goes below, I can panic, for example. Or my contract needs to have a constant variable, or it needs to call another contract. I can assert this condition. If this condition is not there, I can panic. Okay? And nothing else is going to work. I can do a special case when it panics. I can do an error, special case of error, you see? So these would be different treatments for reversions in Solidity, okay? You can give a look more in the documentation for that, which is indeed the homework for today and for the previous lessons. You should read all of those references, all of those links that I have put in this page. There are about 10 or so, about a dozen, if I counted correctly. And if you have any questions, you can create those GitHub issues. I have a small backlog of those questions that I'm going through. And I'm going to answer as soon as possible. You can ping me on the technical channel on Discord too, okay? And we prepare for tomorrow's lessons, wrapping up with the homework. Good? Well, thank you, people. I hope that you have enjoyed. See you tomorrow for more.